everyone. I'm Abhinav. I will be chairing the next two talks. So our next talk is by Sebastian and Wenchen on learning to navigate in challenging environments from simulation to real world. I have to do two brief bios now. So Sebastian is an associate professor at the Robotics Institute at Carnegie Mellon University. His research focuses on enabling autonomy for unmanned rotorcraft to operate at low altitudes in cluttered environments. Dr. Scherer received his BS in computer science, MS, and PhD in robotics from CMU in 2004, 2007, and 2010. He's a Cyber Scholar, recipient of multiple paper awards and nominations, including the AIAA at Infotech 2010 and FSR in 2013. His research has also been covered by many national and international press. And we also have Wenchen Wang, who's currently a project scientist at the Robotics Institute. She received her PhD in Robotics Institute at Shanghai Jiatong University in 2017 and her bachelor's degree in mechanical engineering at East China University in 2009. Her research is focused on applying machine learning techniques to improve perception planning and control. So with that, I would give the talk to Wenchen and Basti.
Thanks for the introduction.
Thank you.
Cool. So I'll just give a little bit of a kind of motivation and introduction, and then Wenchen's going to kind of dive into some of the things we've been looking at. So if you could go to the next slide. So I'll start with some of the challenges, and then we'll go into kind of two ideas that we've been looking at in terms of how we can improve current techniques and some of the ideas. Next slide. Next one. So one of the problems we've been looking at is trying to improve state estimation in challenging situations, especially with environmental degradation such as dust and smoke and fog. And so traditionally SLAM techniques focus a lot on accuracy, and it's the advantage is it's easy to measure accuracy, and data sets often kind of are collected in these benign environments, and that's what a lot of the research is focused on. But for the kinds of tasks that we're interested in, we're often more interested in having a robust estimate, and we're okay with some drift or some inaccuracies. Go to the next slide. So here's just an example of some of the type of operating environment we're in. So this is inside a limestone mine here in Pennsylvania, and you can see the robot kind of autonomously exploring this cave, and as it's moving around, it starts kicking up more and more dust, and so the system needs to be able to handle this. And so there's it comes in, of course it comes into the into the planning algorithm as well, but in terms of state estimation, there are of course also a lot of challenges. And so so the other direction we've been looking at is how can we make this interaction between the robot and environment, how can we model that better? The traditional approach would be to just, let's say, some sort of semantic segmentation of grass, tree, trail, rock, and so on, and then use that map for navigation. But that's often not sufficient to achieve high performance. And so, like how well you can traverse terrain depends, for example, on your speed and your approach angle. And sometimes you don't really know what's under there. So we want to improve that modeling. And so one of the ideas we've been looking at is, can we somehow build some approximation of the underlying physics that based on the information we see. So kind of link it explicitly to what interaction we expect to have. And so the can go to the next slide. And so the so one of the ideas that we've been pushing on a lot is, can we take simulation and translate the results and the data we collect there, or the simulation we run, and translate them onto actual robotic systems successfully. And so in these kind of two directions, on the state estimation side as well as on this off-road driving side, that's kind of been one of our big pushes, is building data sets that are hard enough to be representative of what we, and realistic enough of what we will see. And then also on the off-road driving side, can we make these simulations to be representative of what we would actually see in the real world, and what are the differences, and will this work, or how do we do this transfer and adaptation? So I guess next I'll hand it over to Wenchen, who will kind of go into more the details of the three pieces.
Thanks, Basti. So I'm Wenshan. I'm going to talk about some recent directions in our lab in understanding the challenging scene in unstructured environment. So the first thing we've been looking at is how to improve the robustness of the state estimation and scene understanding. So first thing we look at is what is the existing data sets and benchmarks in the SLAM and state estimation. So we found the existing data sets are a little bit too clean. So for example, these three are the very popular data sets for SLAM. So if we look at the state-of-the-art algorithms, we can see people are competing over very high accuracy down to 0.001 precision. But when we deploy these algorithms on the real vehicle or drone, it usually fails in all kinds of ways. So I think, one problem for this data set is the lack of diversity, and each of the data sets only covers like one or two types of scenes, and they relatively simple. They didn't cover a lot of the challenging cases. Besides, they provide a relatively small number of label data from the perspective of deep learning algorithms. Another thing is the motion patterns in these data sets are constrained by the data collection settings. For example, the kitty is collected by a car, so it is just moving forward in small turn. So if you look at the analysis we've done here, so for the translation and rotation, there are only like one dominant axis. So if you train the models, like learning-based models on these data sets, it's not going to generalize to other type of motions. So therefore, we'd like to create a data set like with these two objectives. So we're going to have a diverse to have a data set with diverse testing scenarios and a lot of challenging scenes and diverse motion patterns, as less bias as possible. And we'd like to provide a large number of label data to facilitate the learning-based methods. So therefore, we utilize simulation data to realistic simulation environment air scene, which is based on Unreal Engine, to provide to create this Tartan air data set. So so our main feature is large size. We collect data in more than 20 environments, and which contains more than 400,000 frames. And we have diverse motion patterns because we don't have the hardware to constrain the way the camera moves. And we provide multi-model labels, including RGB, depth segmentation, optical flow, and pulse. So this has already been published last year. So in this year, so we've been also trying to extend this data set with even more environments, more data, more modality, and less biased motion patterns. So yeah, we've been working on collecting more data in more than 100 environments, and we are targeting more than 2 million frames. And we are adding like IMU, LiDAR, spherical camera, fisheye camera, event camera, and radar. These modalities all into the data set. Yeah, another focus is the challenging features. Yeah, and we've been trying to add like dynamic objects and all kinds of illumination changes, those challenging features that we will encounter in the real world. So we also provide these semantic labels. So in the first version of our data set, so we have semantic labels that are randomly assigned for each environment. So in the second one, we improve the labels by manually relabel the objects in different scenes. So the labels are now come with specific semantic labels. So we as we shown like here on the right side, there's a list of like labels to provide precise semantic information. Yeah, so this shows the challenging features. So we added to our data set. So in all like within 100 environments, we have quite significant amount of environments that comes with these features, including the lighting condition change, the day-night scene, and adversarial weathers like snow, rain, fog, dust, and also dynamic objects like people, animals, and cars. Yeah, so the next thing we've been looking at is can we utilize this data set to do more robust state estimation? So first we looked at like how the previous learning-based methods perform. So in terms of this visual odometry task, we find like learning-based like end-to-end trained model usually perform well on the training data, but if you move it to the other data sets or the real world data, it cannot generalize. The problem is, as we talked about, the training data first is relatively small, like before our data set, and lack of diversity. And they also neglect some of the fundamental natures of the problem. For example, for the monocular visual odometry. So we have to take account of the camera intrinsics in order to compensate the difference between the camera models in different data sets. Also, for monocular odometry, like people doesn't take care of the scale and ambiguity, which will also make the model like, unable to generalize. For example, different data sets have different field of view, different resolution. So if you don't take care of these features, they're not going to generalize. So what we proposed for the learning-based model is to explicitly handle these three problems: the scale ambiguity, and increase the training diversity, and handle the camera intrinsics. So we designed this simple architecture based on the idea from the traditional geometry-based algorithms, which divide into the matching network and post network. So our network, so if we, so first thing we are trying to solve is to look at the scale ambiguity. So if we train this model just without considering the scale ambiguity, we find there's a significant gap between the train and test curve. And we further plot separately the training and testing curve. We can find the gap is mainly caused by the translation. So which indicate that there's a scale issue, like in estimating the exact translation translation motion. So we designed this up to scale loss function, which means we only care about the direction instead of the full scale of the camera motion. So after we doing this, we can see here we has a decrease. We eliminate the gap between the training and loss and testing. So the second thing, so we've been evaluating here is to see how the diversity of the training data can help their generalization ability. As we expected, as we increase the amount of training data, we can see the gap, the generalization gap is also decreasing. The last problem we are trying to tackle here is the intrinsic capability. Like different data set is collected with different camera models. So we need to take this into account. So our solution is to take camera intrinsics as another input. So we designed intrinsics layer, which is a 2-channel tensor encoding the intrinsics in X and Y direction separately. So after we do these things, we can see that our proposed pattern VO model can be directly generalized to unseen data sets. So we tested, we only trained it using our pattern air data sets, and we tested directly without any fine tuning on the KT data set. And we can see compared with learning-based and geometry-based methods, our pattern VO achieve results that is comparable with results. And also in a more challenging like URC and our pattern air data sets, we can outperform the geometry-based methods. So we are more robust to their failures and those challenging features. So here we show some examples. So these 3 trajectories are from our data set. You can see there's a lot of illumination change and moving, like falling leaves. Those features, which is typically challenging for monocular algorithm. And this red line shows the performance of SLAM or ORB SLAM, and our ORB SLAM are shown in blue, and our algorithms are shown in red. You can see ORB SLAM usually takes some time to do the initialization, and also when the lighting change, it tends to like lose track. But our algorithms can track the whole trajectory like more robustly. So here's some more examples from our data set. Yeah, so we've also, we can also generalize to other data sets. Like this is tested directly in Europe data set, so which also has some challenging features like the changing illumination. So yeah, we can estimate the trajectory like quite robustly. Yeah, so we've also been like apply our trained model on the real world applications like the off-road driving task. So what we have here is the serial pair of the input. And so this shows the odometry, video odometry we estimate like in the real world, like also like without any fine tuning. So we can estimate this state of the robot and build a dense point cloud like this. So for the off-road driving task, so we've been mapping the environment using our model, and we build this top-down view of height and RGB colored map, which can fed into our model to the next step, which is understand the dynamics between the robot and the environment. Okay, so at last I'll briefly talk about the how we are going to learn the physical interaction between the robot and the environment. So based on the geometry and semantic information, so previously we've published this scene understanding data set in off-road environments. So called Yamaha CMU off-road dataset, which provides the semantic labels. So based on the geometry and semantic information, we planned a path to keep the robot on track and avoid obstacles. However, so as we mentioned, so this is insufficient when we move to more challenging terrains where the physical interaction becomes more important. So we are trying to understand the interaction. So recently we've collected this large-scale interaction data set called Tartan Drive, so which contains also large amount of interaction data and with multiple modalities, including here IMU, RGB image, stereo input, and a shock travel sensor, which measures the suspension of the wheel, and wheel encoder and GPS signal, those modalities. We collected the data in all kinds of scenarios. Yeah, this just shows for example, of our environments. And yeah, this shows the modalities contained in the data set. And compared to other existing data sets, so our data set is at least one magnitude larger than existing ones. Yeah, so we collected in various terrains like puddles, mud area, grass, slope, gravel. So we are trying to to build a model. So we just the column here. The prediction is made by our model, and the red curve is actually the real trajectory executed by the robot. So given the sensory input and the sequence of action command, so we are trying to estimate the future trajectory, basically how the robot will going to interact with the environment. Yeah. So our data set is available here. So as a summary, so our goal is to increase the robustness of state estimation in unstructured environment, as well as to improve the understanding of dynamics between the robot and the environment. So we published 2 data sets for the above purpose. One is Tartan Air, trying to improve the robustness of state estimation and sea understanding, and the Tartan Drive trying to reason about the physical interactions. So we've shown that we use this data set, some preliminary results on like how can we improve the robustness, as well as this model for understand the dynamics. Yeah, thanks.
Okay, thank you, Wenshan. Do we have questions? So there's a question in the chat. My only question is about the fusion of multimodal data and its synchronization. How's that done? I guess this was in terms of the data collection.
Yeah, for the Tartan Air, because we do utilize the simulation environment, so yeah, we explicitly synchronize the data. So like for like very precise with very precise like timestamp, because we can pause the simulation and collect data and then unpause that. So all the data are like well synchronized. Yeah. So for the drive scenario, so we haven't been able to synchronize to process. Some of the sensors are synchronized, but yeah, but not like exactly synchronized for example the camera and the travel sensor. But we provide those time labels, timestamp labels.
Yeah, so I think the camera, IMU, LiDAR, GPS are synchronized. The shock travel sensor, wheel sensors are more loose. There's some, yeah, there's probably a little bit of jitter.
Yeah.
Any more questions from the audience? Maybe I have a question. In the VO approach, you had one approach where you take the intrinsic camera matrix as the input, right? I was wondering if you thought about decoupling the metric reasoning from the deep learning. Then in that case, you also wouldn't need the intrinsic camera matrix, right?
Decoupling the.
So yeah, so this is an end-to-end approach, right? So this is why you kind of constrain. So if you do only feature matching with the network, and then do the pose estimation using any traditional approach, then you kind of get over. So do you have any idea? I mean, do you have any idea if taking the intrinsic matrix as input is probably better or worse than decoupling this in any other way?
Yeah, I think there's a lot of work existing, like as you said, decoupling the feature matching and use traditional geometry-based methods to do to recover the motion. Yeah, there's some work there. But what we find is providing the intrinsic information and doing this end-to-end, also like estimate user network instead of like geometry way. Yeah, we can also improve the robustness of the post estimation, like using this this end-to-end structure, especially when we add these two layers. So we also do data augmentation to generate the data with different camera intrinsics. So by doing this, basically the network is capable of solving the camera motion with different camera models. So this like improve the capability of the post network. So we can compare like only train with one type of intrinsics, train this model with only one intrinsic setting versus multiple like random setting. If we train it with like multiple intrinsics, it becomes more capable and more robust. So yeah, I do think that adding intrinsic there, although making it harder for the network to learn, but make it like more robust, more general.
Okay, thank you. I don't see any more questions. With that, I'd like to thank the speakers. Thank you, Wenxuan and Basti.